So, water is probably the most important molecule for living things, and it has some very unique characteristics. First of all, some molecules are nonpolar. In a nonpolar molecule, there's an even distribution of all the electrons in a molecule. And so um, the molecule itself is neutral, and the all parts of it have the same kind of distribution of charge. And that's what these diagrams are trying to show, that everything is distributed equally within these molecules. And so we talked about covalent bonding in our last slideshow. And this would be a non-polar covalent bond where um, the sharing is happening equally by both dogs in this case. Now, water actually is a polar molecule. And in a polar molecule, there's an uneven distribution of electrons. And so these diagrams are showing how water is polar, where we have a different distribution of the electrons. We have more over here and less over here. In a water molecule, more electrons are near the water edge and fewer electrons are near the hydrogen edges. And so even though water overall is a neutral molecule, one edge of it is a little more negative and the other edge of it is a little more positive because of polarity. So overall molecule's neutral, one side's a little more positive, the other side's a little more negative. And so it's showing that this would be nonpolar, where we look like the distribution is equal on all parts of the molecule. This is polar, where we can see that we definitely have a different distribution on this side than we do with that. Now, because water's polar, it gives it some really unique characteristics. So first of all, if we use our dog covalent bond example again, if it's polar, we have a larger dog and a smaller dog, and the larger dog is doing more pulling, but they're still sharing the information. And so that's what we see here. With a polar bond, a polar covalent bond, they're still sharing all the electrons. It's just that one part of it seems to have more of a hold on them than the other, but it's still a really strong bond. So because of water's polarity, it's able to form these weak hydrogen bonds that we talked briefly about in the last slideshow. So the positive ends, the ends where they have the hydrogen, and the negative ends of a completely different molecule, the oxygen part, are going to become attracted to each other. And we can see this here, how this starts to link up the different water molecules and create a water molecule chain. And keep in mind that these are really weak bonds, but it is kind of holding them together in kind of a sheet sort of a way. And here you can see how they can all arrange themselves in a really organized orientation. So because of the hydrogen bonding and the polarity, one characteristic that water has is cohesion. And I really like this diagram here because it's got two little water molecules holding hands. Cohesion means that water is attracted to itself. It's the attraction between like substances, between like molecules. So water can bind with itself. So surface tension and raindrops are all examples of where water attaches to itself and we end up with a formation because of that. So cohesion explains droplets of water. So here we've got that water that is just like an independent drop all on its own, and that's because the water molecules are being held together. Same when we get water dripping like out of a faucet. This is surface area or surface tension, excuse me, where it's almost like those water molecules have created a floor for that insect to walk on. Now, remember, these bonds are really, really weak. And so that's why we can't walk on water like this because our weight is just too much for those hydrogen bonds. But these really light insects are able to do that. If you've ever gone swimming and you decided you wanted to try diving and instead you ended up doing a belly flop, the reason a belly flop seems to hurt so much is because when you are horizontal, either on your front or your back, if you've ever done a back flop, and when your body hits it, you're hitting that surface of the water. And your entire body takes that impact all at once, and you can feel that and it slaps against the surface of your body. Where if you were to dive and you have your hands going first, your hands are able to break those hydrogen bonds apart, and it almost creates like a little hole in the water for the rest of your body to dive into. If you've ever put drops of water on a penny, you can see how big the drop can end up getting. And here you can even actually see it almost going over the edges of the penny. That is because water is sticking to itself. And then eventually, if you do that and you put so much water that the water is getting too heavy for itself, it will spill off of the penny just like that. And that's when it breaks that surface tension. It breaks those hydrogen bonds that are causing that cohesion. Another characteristic of water, because of polarity and hydrogen bonding, is called adhesion. And adhesion, I really like this diagram. We've got our little water holding hands with something else. And that's what adhesion is. Water being able to hydrogen bond and stick to a different surface. And so it would be these water molecules sticking to whatever surface this is. For example, when you take a shower and you turn off the water and water has beaded up all over your body and it's beaded up all over the walls of the shower. That's adhesion because the water molecules are sticking to the surface of your body and they're sticking to the surface of the shower. You don't absorb water when you shower. You're not a sponge. Your body's actually waterproof, which is why then it ends up beating up and adhering to your body like it does. Here are some other examples of adhesion, like when we get water droplets that stick on a spider web. If you've ever tried to pour out of a glass or cup of water and you end up spilling all over the side, and that's because as you pour, the water sticks to the edge of the glass and starts dripping off of that side. And then this is a neat little experiment. They have a glass of blue water and they have a glass of yellow water, and they put a paper towel in the blue towards the middle and then a different one in the yellow towards the middle. And because of adhesion, the water actually goes up the paper towel and then down the other side into the empty cup. And it starts to fill that empty cup with blue water and yellow water, which eventually turns into green as it mixes together. Something that's really interesting is called capillary action. And capillary action is a combination of cohesion and adhesion. And it's when water is able to stick to itself and stick to narrow places and appear to move in opposition of gravity. If you remember doing experiments in middle school when you had a graduated cylinder and you had a meniscus form, and they said when you're measuring with the graduated cylinder, you always want to read the bottom of the meniscus. The reason that meniscus forms in the first place is because water sticks to itself and it starts sticking to the edges of the glass graduated cylinder. And so we have water sticking to itself as well as water sticking to the graduated cylinder. Because of adhesion and cohesion, giving capillary action, if we take a really narrow tube and put it into liquid, it'll just rise up the tube on its own because the water is going to stick to itself and start sticking up the sides of the tube. And so it's not like anybody is drawing that water up the tube, it's doing it on its own. The narrower the tube, the higher up the water is able to travel on its own because there's less area for the water to not be able to stick. Here you can see the same sort of thing that this animation is showing, and you're actually able to color white carnations because of capillary action. If you take a white carnation and put it in food coloring, that is going to go up the inside of the stem and eventually deposit the coloring in the flowers. And so what they did here is they have blue and they have red. So they have one flower in the blue, they have one flower in the red, and then they took a third flower, they cut the stem up the middle in half, put half the stem in blue and half the stem in red, and it actually colored half the flower blue and half the flower red. So that's all capillary action. Now, water purity will influence how well water can form these hydrogen bonds. The more pure the water, the more hydrogen bonds are able to form. As soon as we add impurities to the water, it's not going to be able to form hydrogen bonds as well. And that's because if water is pure, there's only space for those hydrogen bonds to form. But as soon as we add in impurities, like if we were to add salt to the water or soap to the water, now the water is not as pure, and those soap or salt molecules are getting in the way of those water molecules forming those hydrogen bonds. And so the more impure the water, the less sticky the water becomes. So as solutes are added, harder for water molecules to hydrogen bond with itself or with something else, it reduces cohesion and adhesion. So here's an example with a little insect that's walking on water. We've got surface tension because of cohesion. If we add a little salt to the water, it's going to cause some of those hydrogen bonds not to be able to form. And the insect starts to have a little more difficulty walking on the surface of the water because the surface isn't as strong anymore. With more and more salt added, there's less and less hydrogen bonding, less surface tension, and eventually that insect's not going to be able to walk on the water anymore. We have added so much impurity that there's no longer that cohesion that allowed it to walk on the surface. Other characteristics of water: if we don't have pure water and we have something distributed or dissolved in water, that's actually a solution. And in a solution, we have a solute. The solute is whatever we're planning on dissolving, and the solvent is what is going to do the dissolving. Most often, our solvent is water. We take solute of salt and dissolve it in water, our solvent. We take the solute of Kool-Aid and dissolve it in our solvent of water. The solvent doesn't have to be water. In living things, it almost always is water. But let's say you wanted to make Kool-Aid that was sweeter and more carbonated. And so you took the solute and you dissolved that Kool-Aid in Sprite. Sprite would be the solvent because it's going to help that Kool-Aid get dissolved. When we have solutions, we can measure them according to their pH. And pH has to do with the amount of hydrogen that's in the solution. If we have a neutral solution, it means that hydrogen and hydroxide are equal. Now, if you look, if we have a hydrogen and we have a hydroxide and we put those together, we end up with H2O. We end up with water. So water is neutral because it's going to have equal amounts of hydrogen and hydroxide. But if our solution has more hydrogen ions, it's an acidic solution. And oppositely, if we have a solution that has fewer hydrogen ions, that's going to be a basic, sometimes called an alkaline solution. The pH scale is a scale that we can compare the pH of different substances. The pH scale has these different numbers on it. Each number is stronger or weaker than the next by a factor of 10. So a jump of a number on the pH scale is actually a huge jump. Now the pH scale starts at 0, it ends at 14, and the middle is 7. Now the best way to think of the pH scale is actually to think of it as 7, which is neutral, as kind of our starting point, even though it's in the middle. The further away we work from 7 in either direction, the stronger and stronger we get. Anything that's less than 7 is an acid, where it has a lot of those hydrogen ions. Anything with a pH greater than 7 is a base, where it has less of those hydrogen ions, but more hydroxide. And if you are having a difficult time remembering, you have acids and bases and where they go on the pH scale, think of the alphabet. A comes before B. So when you're looking at the pH scale, acids are going to be on one side and the bases are going to be on the other in the same direction that you would read. So if we look at the pH scale and some common substances, water is pure. All of these things are bases. Bases, you'll notice oftentimes have to do with cleaning supplies. A lot of these up here help clean. Acids are less than 7, and a lot of these are fruits. It just happens to be that fruits are more acidic. Things that help us clean tend to be more basic. pH of 1 is going to be much stronger than a pH of 5 because a pH of 1 is further away from 7. A pH of 13 is much stronger than a pH of 9 because it's further away from 7. We only want to compare bases with bases and acids with acids because they're very different substances. If we were looking at a pH of 2 and a pH of 3, 2 is stronger because it's further away from 7. 2 is 10 times stronger than 3. Okay. If we were going to compare 2 to 4, like a lemon compared to a tomato, 2 is stronger. It's a stronger acid because it's further away from 7. And it's 2 numbers away on the pH scale. So that is 100 times stronger. A lemon is 100 times more acidic than a tomato. If you're not sure how we did that, it's a factor of 10. So the difference between pH 2 and pH 3 is 10. The difference between pH 3 and pH 4 is 10. We don't add those, we have to multiply those. So 10 times 10 is 100. If we wanted to compare a lemon at a pH 2 with a banana at a pH of 5, 10 times 10 times 10 is 1,000. So a lemon is 1,000 times more acidic than a banana. One last thing about the pH scale is if we combine acidic substances and basic substances, they are going to come closer towards the center and become more neutral. So if we took something that was a pH of 6 and something that was a pH of 8, if we combined those, we'd end up with a neutral substance with a pH of 7.